Today's lecture is going to talk about iterated expectation, multivariate normal distributions, and we're going to talk at the end for a bit about bivariate transformations. And we'll continue talking about bivariate transformations into next lecture also. So to start, we're going to talk about a theorem, and the theorem is called the theorem of iterated expectation. So let's write that, iterated expectation. And this is really going to feed off of the conditional expectation that we talked about last time, and we did some examples with. And I'm going to first write out the theorem, and then we're going to talk about the parts of it and kind of explain what it means. So we're going to have some new notation. I'm going to say that if x and y are random variables, then the theorem of iterated expectation says that the expected value of x can be written as the expected value of the expected value of x given y. So that's the theorem. And it's a pretty short theorem, but it packs a lot into it. So let's kind of step back and let's analyze the parts of this. So the first thing to recall is what conditional expectation is. So previously in the last lecture, we talked about conditional expectation. And so we would write something like the expected value of x given y is equal to little y. So capital X and capital Y are random variables, little y is some number, right? So here, little y is some real number. And in the continuous case, this was, we integrate over the whole line of x times the conditional PDF of x given little y, and we integrate with respect to x. So the only difference between the expected value of x and the expected value of x given y is equal to little y is we replace traditionally the PDF of x with the PDF of x given y, the conditional PDF. So note that this whole thing, just like every other expectation we've worked with so far, this whole thing is just a real number. This expression, it's an integral, right? It gives you a number at the end of the day. And so for each little y I could choose and condition on, I get some expected value of x given my random variable y is at little y, which is also in R. It's also a real number. And so this defines, we might say this defines a function, and maybe you'd call the function g. It's a real valued function that takes in real numbers and spits out real numbers, where we could say g of y is whatever this conditional expectation is. So this is a kind of weird function to look at, and we'll relate it back to our theorem, so don't lose sight of the theorem we're talking about. But it's a function. You could look at all the different values of expected value of x condition on y is equal to little y for all different values of little y, and that would give you a function. It would give you a real valued function. We call it g. What you could do, so this is just some function. Depending on x and y, it's going to be a different function. But we could take our random variable y, and we could plug y into g. Last time, or a couple lectures ago actually, we looked at transformations. So if we plug y into a real valued function g, we get g of y, which is some transformation of y. And you could do that generally with any real valued function, and so we could do it specifically with this function we defined. So g of y here would be basically what I would get if I take expected value of x given y is equal to little y, but where I'm plugging in for little y, I'm going to plug in my random variable big Y. So you might be tempted to write it like that, where I'm replacing little y with a big Y, it's kind of a weird way to write that. So notationally, what we tend to write is we write x given y, x bar y, and we drop the little y. But at the end of the day, this is just notation. And this is notation for if I form this function g of y, and I plug my random variable y back into that function, what I get we denote as the expected value of x given y. So a couple things to note here, most important being that this is a random variable, right? Y is a random variable, a function of y is a random variable, and so g of y, or expected value of x bar y, expected value of x given y, is also a random variable. It's a random variable, and it's a function of my random variable y. So it's some function of y. So it's some random variable based on y. So we kind of have these two concepts that you got to keep straight in your head. The first is the expected value of, let's say, x given y is equal to some value little y. And this is a number. I choose my little y, and this spits out a number, just like expected value. We then have this notation, expected value of x given y, close bracket, and this is a random variable. So it's real important to keep these two concepts separate. Okay. So it's a bit weird of notation, but it's really kind of useful notation, and this is standard in probability. So if you don't understand that difference, take a minute, back up, and see if you can figure out what's going on here and rewatch what I just discussed. So let's go back up to our theorem. It says the expected value of x is the expected value of x given y. So let's write that down. On the left-hand side, we have expected value of x. X is a random variable. Expected value is just like the normal, typical normal expected value. And on the right, we have this expression. Expected value of x given y. So this is called the theorem of iterated expectation because we're iterating, or we're applying twice this expected value. So the argument here in this expected value is a random variable. It's just some fancy notation for a specific random variable we're considering. And so it has an expectation, and so it makes sense to apply the expected value operator to it. And it will give us a number, which matches what we have on the left side, which is some other number. Okay. So that's the theorem. It says that if I take the expected value of x given y, and I kind of view that not as a number, but not as a function of y, but as a random variable function of y, and then I apply an outer expectation. So this outer expectation, sometimes you can write a little subscript y to denote that it depends on y. If you apply the expected value again with respect to y, that will just give you back the expected value of x. So it somehow cancels out the conditioning here. Let's look at a proof in the continuous case. It's actually not so bad of a theorem. And the kind of two facts that we have to, maybe 2 or 3 facts that we want to talk about first, is that if I can get the marginal of x by taking the joint of x and y and integrating out y, right? So if I integrate fxy with respect to y, I'll get the marginal of x. And then we have this other theorem that says that, we'll call Bayes' theorem, right? It says the conditional of x given y, you can write as the joint of xy over the marginal of y. Or equivalently, I could rearrange this and say that I could multiply each side by fy and say that the joint of xy is the conditional of x given y times the marginal of y. So this is something like kind of a compound probability rule for PDFs. And the last thing I want to note here is just remember again, we're going to do this for the continuous case, that the expected value of x given y is equal to little y is the integral of x times conditional x given y, and integrate, let's integrate with respect to x. Okay, so given that, let's do a little proof. And the proof is just going to kind of expand things out and then collapse them back. So the expected value of x, of course, we can write as the integral x fx dx. And I can write fx as, using my first kind of identity here, as the integral of fxy dy. I don't want to forget my outer dx, right? The second thing I'm going to do is that I can write my joint here as f of x given y times f of y. So I'm going to expand that out. I still have my integral dy, and my integral, I have an x, and I have a dx. And I'm just going to play some games now. I'm just going to rearrange some things. So suppose I need an equality sign here. I'm just going to put everything together. It's a double integral. And let's write it dx dy. It doesn't matter the order of my integration. And I'm left with an x, f of x given y, and an f of y. And I can actually pull that f of y out of my integral with the x, because it doesn't depend on x. So I can write this as the integral with an inner integral of x, f of x bar y, dx. And then I have on the outside my things that depend on y. Here, we then use kind of our final fact here, that you should note that this thing is, of course, the expected value, this conditional expected value. This is the conditional expected value of x given y is equal to some little y. And if I had defined this thing to be what I call g up here, g of y, I could also rewrite this as it's just some number, and if I change y, I'll get different values. I call that g of y. And so you could write it like that, and you can recognize that as the expected value of g of y, my random variable. Right? This is the law of the unconscious statistician. And this g of y, again, scroll back up here, was what we had called expected value of x bar y, expected value of x given y. So this would be expected value of, and the notation we use for this is x given y. So this seems like a little sleight of hand, but it's not. It's just rearranging things. And we started off with expected value of x, and we get expected value, the expected value of the expected value of x given y. And this outer integral, again, is the integral, or the expected value with respect to y. Okay, so let's do some examples. That's probably the most straightforward way to understand this. So some of these are going to be familiar. Some examples we looked at last time. Let's consider two random variables, x and y. The conditional distribution of x given y's little y is binomial yp. So p here is just some number, some real number, in 0 to 1. And the marginal distribution of y has a Poisson distribution. Some rate parameter called lambda. I think we looked at this one last time, and we had to do a lot of work to figure out what this was. The theorem of iterated expectation is going to make this really simple, because I could ask you, say, what is the expected value of x? So here are the kind of three steps we're going to follow. First, if I fix y at some little y, let's look at the conditional expectation. Expected value of x given y is little y. X given y is little y is binomial. So the expected value of binomial is the product of its parameters. So that's just y times p. And so you could call this thing, for example, g of y. Now let's form expected value of x given y. So this is the random variable. This is g of capital Y, which you could write as y, capital Y times p. The third step is I want to take the expected value with respect to y of the expected value of this x given y, which is the expected value of yp, and p is a constant. That can certainly come out, and so we get p times the expected value of y. Y is Poisson with a rate parameter lambda, and so we get p times lambda. The expected value of y is lambda, and so our expected value is p lambda. And that is pretty much exactly what we saw last time we saw this problem. I think we actually derived the whole distribution, but if you just want the expected value, that's a really quick way of doing it. So that's a super powerful theorem. Let's look at another example of that. So here's our second example. Let's do kind of something similar. Let's say x given some random variable p is little p. It again is going to be binomial, but instead of our number of trials being random, our probability is random. So n is fixed. This is just some integer. And little p is going to be, capital P is our random probability. Marginally capital P, we're going to say has a beta distribution. If you recall, a beta distribution has two parameters, alpha, beta. A beta distribution is confined to be between 0 and 1 and has some shape in there. So this makes sense for a probability, because probabilities have to be between 0 and 1. And so I could ask you, for example, what the expected value of x is, given the setup, and let's do this one a little quicker. Expected value of x, we know by our theorem, is expected value of x given p. Expected value of x given little p would be n little p, so the expected value of x given big P would be n times big P. And as a constant, I can pull that out, and I just get the expected value of P. Whoops, that's big P. Big P is beta, and so its expected value is alpha over alpha plus beta. That's the answer. That's what the expected value of x is. If x is a binomial with a random probability according to a beta distribution. And that makes a lot of sense, I think, for an answer. Instead of the expected value being np, it's the expected value is n times whatever the expected value of our random probability is. In this case, follows beta distribution. So that's the law of iterated expectation, theorem of iterated expectation. There's a similar theorem, and this similar theorem is called the law of total variance. And it's basically the same theorem, but for variance. So it tells me that the variance of x I can write based on the conditional variance of x given y. And the way to remember it is that the variance of x is the expected value of the variance of x given y plus the variance of the expected value of x given y. So it's the expected value of the variance plus the variance of the expectation. And so here, this thing is similar this conditional variance is similar to the expected value of x given y, right? What you do is you look at the conditional variance of x given y is little y for all possible values of y. That gives you some function. You can plug your random variable into it. So this thing is a random variable also. In the same way, expected value of x bar y is a random variable. Variance of x bar y is a random variable. So you can talk about this expectation. And on this other side here, again, expected value of x given y is a random variable. It depends on y. And so you can talk about its variance. This will make sense more if we do an example. So let's go back to our previous example, all right? We're going to skip the proof. The proof looks a lot like the theorem of iterated expectation. But let's look at our previous example. So again, x given p is little p follows a binomial distribution and little p, and marginally p has some beta distribution. And I could ask you, what is the variance of x? So we need to find a couple things. First of all here, well, let's change colors. Let's gather together a couple things. Expected value of x given p is little p is, of course, n little p. And the variance of x given p is little p, similar thing. It's n little p times 1 minus p, right? It's just a binomial distribution, so it just follows those rules. And so if we wanted to look at our concepts of x given p is n capital P, and the variance of x given p is n capital P times 1 minus p. And so the theorem, law of total not expectation, total variance, is that the variance of x is expected value of, expected value of the variance plus the variance of expected value. So the variance of the expected value, this is the expected value of n p times 1 minus p. Now the capital P is a random variable, and the variance here is variance of n times p. So this variance term is pretty easy. N comes out, gets squared, and we're left with the variance of p. In the expected value case, the n comes out, and we're left with the expected value of p minus expected value of p squared, right? I'm just going to square that out. And I won't fill in all the details here. I will give you kind of the shorthand proof, which is there's some algebra. So you have to look up the first two moments of a beta, and this should give you n, of course, and it's going to be alpha beta over alpha plus beta plus 1. So you have to look up the first two moments of a beta and then take the difference or derive them. And then we n squared, and the variance of a beta is alpha beta. Almost the same thing, but it's alpha plus beta squared alpha plus beta plus 1. So there's a couple steps I'm skipping, but you add those two together, and that's the variance of x. So it's a little more complicated, but it kind of follows similar rules. So those are that's kind of finishing up with iterated, with conditional expectation, conditional variance, with the theorem of iterated expectation and the law of total variance. So we'll see some problems on those. The next topic we want to talk about, kind of changing gears here, so this lecture is a little bit of a transition lecture, is we want to talk about the bivariate normal distribution. So this is kind of changing gears. Okay. Good place for a break if you need one. bivariate, oops, let's spell this right, bivariate normal distribution. So we've talked about the univariate normal distribution, and has this classic shape, right? So that if we look at the PDF, it has this classic bell shape centered at mu, and the width of the bell is related to the variance, sigma squared. And so it has these two parameters, mu and sigma squared. And its PDF fx is 1 over root 2 pi sigma squared exponential of negative 1 over 2 sigma squared x minus mu squared. If you do probability of statistics long enough, that gets burned into your memory indelibly. So the bivariate normal is, of course, the extension of a normal distribution to 2 dimensions. So now we have to draw a plane. We have 2 random variables, x and y. Let's put our coordinate system like this. So this is fxy. This is our joint PDF. And it kind of forms this like 2-dimensional real bell shape. So it kind of looks bell-shaped kind of in all directions. It looks like a real bell. And you could think about the contours. The contours kind of go around like this. So it's this kind of, my 3D drawing's not so good, but it's this kind of bell shape here. And it's going to have a couple of parameters. It's going to have a location parameter, which often gets denoted as just mu, but this is a 2-dimensional parameter. So it's a mu x and a mu y. So it's the 2 coordinate position for the center of it. And it's going to have also a sigma squared x and a sigma squared y, which kind of tells you in the x and y direction how stretched out the bell is. And then it also has a parameter rho, and rho is going to be the correlation. And if you were to look kind of top down at this thing, you could see a couple different scenarios, and you look at the contours. So this kind of center of it is at mu, and then it's going to have the contours. And if the contours are kind of really elongated between x and y, this is rho is much bigger than 0. So it's a correlation between 0 and 1. If our contours, so here again is our center mu, look kind of like this, this is going to be the case of a high negative correlation. And of course, the final case could be that if I have contours that kind of look like circles, they're not really elongated in a direction. This is going to happen when the correlation is about 0. So basically, the correlation, of course, tells you how much x and y move together and how much they're correlated, how much they're related. And it tells you kind of how elongated and stretched out these contours. So the contours are always kind of ellipsoidal, and rho tells you how squished they are. The bivariate normal has a PDF, and there are a couple ways to write it. I'm going to write it in one way. Let's write it 2 ways. So first, I could say that x, y, I could say bivariate normal, and it has a couple parameters, right? It has mu x, mu y, sigma x, sigma y, and rho. So this is one way you'll see it, often in some kind of lower level undergraduate textbooks. I'll tell you why I don't like this, but it's a valid way of writing it. In this case, and sometimes it's really useful, the PDF fxy takes the following form. It's 1 over 2 pi sigma x, sigma y, square root of 1 minus rho squared, exponential of negative 1/2 times 1 over 1 minus rho squared. And then we have x minus mu x over sigma x quantity squared plus y minus mu y over sigma y quantity squared. It's supposed to be a sigma y. And I'm going to go down here and minus 2 rho x minus mu x over sigma x times y minus mu y over sigma y. And then I got to close up all my params. That's one way of writing it. And you can see some of the analogies to the univariate case. It has kind of similar feel in many ways. The more kind of adult way of writing this, and I'm going to say simpler because it will allow you to generalize this to more than 2 dimensions, is you work with the mean vector mu, which consists of mu x and mu y. And then you work with something called capital sigma, which we call the covariance matrix. So let's just write that down, covariance matrix. And sigma encodes the variances on the main diagonal. So it's a 2 by 2 matrix. On the main diagonal, we have sigma x and sigma y. And then on the off diagonal, we have the covariance, which is going to be sigma x, sigma y rho, sigma x, sigma y rho on the 2 off diagonal. So the covariance matrix is literally, another way of thinking about it is that it is variance of x, variance of y on the main diagonal, and then covariance of x and y and covariance of y and x. Of course, covariance is symmetric, so that gives you the same thing. It encodes all the information about the parameter rho and the variances. And so you can go and you could get rho from this. You can certainly get sigma x and sigma y as the diagonal. You could then get rho by dividing through the off diagonals by the standard deviations. So you could get back the parameters, but it's a nicer parameterization if you put this as a mean vector mu and a covariance now matrix, because it allows you to write the PDF in the following way. If I let z be the 2D vector x comma y, then f of z, or f of xy, is 1 over 2 pi, 1 over square root of the determinant of sigma, my covariance matrix, exponential, negative 1/2, z transpose, sigma inverse z. So that takes a lot less time to write than the form up here. And it's really compact, and it allows you to actually, very good naturally, we'll see in a couple lectures, you can extend this to more than 2. You can have a trivariate or whatever, multivariate normal distribution. Go back and think about linear algebra, and you can convince yourself that this is true, that these 2 ways of writing it are the same. I'll leave that as an exercise to you, but it's a really nice, compact way of writing it. So let's think about some facts. Let's discuss some facts about the multivariate normal. So 2 facts that you have no problem believing. Let's say first fact is that the marginal of x is distributed normally with mean mu x and variance sigma x squared. And similarly, the marginal of y is distributed mu y sigma y squared. So if you want to get the marginals, you just forget the parameters that, or you just look at the parameters that depend on x if I want the marginal for x, and this is also normal. Second fact you'll believe is that the correlation between x and y is rho. So I claim that that's a correlation, and it shows up either here in this PDF this way, or it shows up in my covariance matrix here. The fact you'd actually have to show, but my claim is true, which is that that thing is the correlation. A third fact is that if I look at a linear combination of ax plus by, that is also normal, and it has a mean a mu x plus b mu y, and a variance a squared sigma x squared plus b squared sigma y squared. But then I also have to account for the covariance, so it has you have to add on 2ab sigma x sigma y rho. That's a little bit of a mouthful, but it's concerning that any linear combinations of the elements of a bivariate normal is also bivariate normal. It has kind of formulas, if you go back and look at our lecture on covariance or variance of a summation, this part is going to look familiar. A kind of more theoretical fact is that a characterization of the bivariate normal is that x, y has a bivariate normal distribution with whatever parameters if and only if for all possible numbers a and b, ax plus by is univariately normal with whatever parameters. So we kind of said the partial to this, which is that if it's bivariate normal, then a linear combination, and all linear combinations are univariate normal. The reverse, the converse is also true. If for every possible linear combination of two random variables, they are normal, jointly they are bivariate normal. And this is actually a characterization of bivariate normal. You could define it by giving the PDF above, like I had, but you could also just state this brute fact, say, okay, bivariate normal is any distribution for which any and all linear combinations of it are, the two components are normal. So if you give me two random variables and every linear combination of those normal, they are jointly bivariate normal. So it's a really powerful theorem. A little beyond the scope of this course to prove, but it's nice. Okay, the last fact is a really nice fact. And we'll actually do a proof of this one. Short proof. If you recall that previously we said that if x and y are independent, then the correlation between x and y is 0. So independence implies 0 correlation. And we said generally it's not true. The converse isn't true. If the correlation is 0, you don't know they're independent. Except if they're bivariate normal. If jointly x and y are normal, then this is an if and only if theorem. So we kind of have a partial converse of this theorem, and this is actually only true of normal. If x and y are some bivariate normal, and the correlation between x and y is 0, then x is independent of y. So it's a kind of partial converse in the case of normality. This is really important and super cool, and is only true of the normal distribution. That we get this partial converse, where normally independence implies 0 correlation, but the other way isn't true, unless things are jointly normal, they're bivariate normal, then correlation does imply independence. So correlation and independence are the same concept for bivariate normal random variables. Let's do a proof. It'd be a good exercise in rewriting our PDF. All right, so the PDF of x and y for bivariate normal, let's see if we can get this on one line, is 2 pi sigma x sigma y root 1 minus rho squared. It's supposed to be a rho. All that's in the basement. And then we have exponential of negative 1/2. We have a 1 minus rho squared in the basement. And then we have x minus mu x over sigma x quantity squared plus y minus mu y over sigma y quantity squared plus 2 rho, almost, x minus mu x sigma x y minus mu y sigma y, right? Bunch of friends at the end. Okay, so this is my claim, and my claim is that if the correlation is 0, so rho is 0, right? My correlation is 0, rho is 0, so this thing goes to 1, this thing also goes to 1, and this whole term here drops out. And this allows us to write this as, simplify it, that's our constant out front. I can write this as exp negative 1/2, and I'm going to separate this, x minus mu x over sigma x quantity squared. And I can close friends. Of course, I have to add on my y term, but using rules of exponents, I can write that as a product with another exponent. Distribute my 1/2, y minus mu y over sigma y quantity squared. So you have to believe that these two lines are equivalent. It's just rules of exponents. But what I've cleverly done now is I've separated fxy into a function that depends on h of x, so a function that depends just on x, and a function, maybe call it g of y, that depends just on y. So I've factored the joint into, let me write this down, I've factored my joint into a function of x times a function of y. We had a theorem last time that said this means x is independent of y. And so indeed, correlation being 0 and having a bivariate normal PDF implies that the two random variables, x and y, are independent. We'll see the bivariate normal throughout the course, and we'll talk about, in a couple lectures, we'll talk about what's called the multivariate normal, which is kind of a generalization. For the remainder of this lecture, we're going to talk about everyone's favorite topic, which is transformations. But because doing transformations in one dimension wasn't fun enough, we're going to talk about doing transformations in 2 dimensions. So let's talk about bivariate transformations. So in the univariate case, we had some function g, a real valued function, and then we'd say, okay, if I have a random variable x, what happens if I plug x into some function g? Make sense? In the bivariate case, now we're having fun with 2 random variables at a time, I could give you a function from the real plane to the real plane, and I could say, what if I take this 2-variable function and plug in my 2 variables, x and y? What then? So let's just look at some notation. So that's basically what we're going to talk about today and next lecture. So our notation is that typically the notation we're going to use here is I'm going to have 2 random variables x and y. I'm going to throw them in some 2-dimensional function, g, and I'll get out 2 other random variables, u and v. So example, uv might be x squared y. Pick your favorite transformation, and maybe the second component is log y. So here, my first component, this is what I'll call like g1, my first transformation function, and this is g2, my second coordinate of my transformation. The g1 of x, y, and g2 also takes x and y. So g1 is a function that takes x and y, gives us just one thing, and g2 takes x and y and gives us something else, right? So those are the kind of coordinate functions. We could have other examples. Maybe uv is negative x over y xy. But you can come up with your own examples. So just like the univariate case, let's start by talking about the discrete case. And we'll touch a little bit on we'll maybe set up the theorem and set up the problem for the continuous today. For the discrete case, so again, uv is going to be our transformed random variables, and u is some g1 of xy, and v is some g2 of xy. And assume that x and y are discrete. And define, we're going to use the notation a sub little u little v, basically to be the inverse, it's supposed to be inverse, image of point little u little v under G. So what is that? It's all points x and y such that when I map it, G1 of xy gives me u, and G2 of xy gives me v. Oh, close bracket. So this is the kind of notation. It's just the inverse image. Here's our picture. We start with two-dimensional plane, and we're going to end up in the two-dimensional plane. G transforms us. After my transformation, there's going to be some point over here, little u, little v. And I'm going to ask, what points in my original space map to this point, little u, little v? So maybe this point does, maybe there's a point here that does, maybe there's a point here that maps there. Right, so here are my points. And this set containing them, we're going to call this set A, U, V. Or you could alternatively call it G inverse of U, V. It's the inverse image of the point U, V under G. That's how you want to think about it. So here on the left, we have our X, Y space, and on our right, we have our U, V space. And what we want to do, here's what we want. We want to get we should be careful here, we should call it the joint PMF of U comma V from the joint PMF of X comma Y. So that's basically what we want to do. In the discrete case, if I know the joint PMF of X and Y, and I give you a transformation G, and this transformation gives me two new random variables, U and V, what's the joint PMF of my new ones? And the answer is that, so F, I can say U comma, sub U comma V of little u, little v, so this is the joint PMF of my random variables u, v. This, of course, is a fancy way of writing the probability, so the joint of PMF of u and v at little u, little v, is the probability u is little u and v is little v. And if we go back up to our picture, if we want to find the probability we're at this point, little u, little v, that's equivalently the probability that x and y are in this set A. So we could equivalently say that this is the probability that x comma y are in this set A u v, or in the inverse image. This is pretty much the identical argument we had in the univariate case. So go back and look at that one if this is blowing your mind here, right? So pretty much identically the argument we made. And this is just a discrete random variable, or bivariate discrete, but it's not too bad. So to get that, all we're going to do is sum over all pairs uv that are in this set, and we're going to sum the joint PMF of xy at the left of the y. So all it's going to say is we're going to map back to maybe these 3 points here, and we're going to sum up probability over here, here, or here, using our known PMF of x. It's pretty much identical to the univariate argument we made. Again, I think these things are probably easiest done if we look at an example. So let's look at an example. Let us consider two random variables, x and y, and just to keep us sane, let's make them independent so the things are straightforward. So x is independent y, and x is going to have a Poisson distribution with some rate parameter theta, and y is also going to have a Poisson distribution with a rate parameter lambda, different rate parameter. In any case, these are discrete, and we can get the joint PMF of x and y, right? Because x and y are independent, this is just the product of the two marginals. And we know the marginals for univariate Poisson distributions. If x is Poisson theta, the PMF of x is theta to the x, e to the negative theta over x factorial. And the PMF of y is Poisson lambda, it's lambda to the y, e to the negative lambda over y factorial. So that's our joint PMF, and because they're independent, it's actually pretty simple to get. Now let's make things complicated. Let's define u as x plus y and v as just y. So v is just going to give us y again, but u is going to be the sum of x and y. So, with more heavy notation, you could say uv is g of x comma y, where g1, our first component function, would be x plus y, and our second component function here would just give us y. It's useful when doing these practice problems to think about it kind of in the fully formal context. So, okay, so that's good. So we kind of have the components. What do we need? The components, we need the joint PMF, which we have, and then we need this set AUV. We need to find the inverse image. The hint here is that, so let's say we need AUV, is that if U is x plus y and v is y, then surely u minus v is x, right? And so if we want the inverse image, in this case this is an invertible function, so the inverse image is just the inverse. G is invertible. And typically always G is going to be invertible. Giving you a non-invertible G is a really hard problem. But pretty much in these cases, G is always going to be invertible. So we need to find the inverse, basically, right? So to find the inverse, basically you solve back for x and y, right? Here, I give it u and v in terms of x and y, and I want to solve for x and y in terms of u and v. Well, y is v and x is u minus v. So a sub uv, which you could think of as the inverse of uv, should be xy, u minus v, v. Whatever way you want to think about it, that's what we're calling a sub uv here, the inverse image. So back up to our picture here, that gives us the point that maps to uv. In this case, it's invertible, so only one point maps to uv, and the point that maps to uv is u minus vv. Notice that if I plug that in, back into my function, u minus v plus v, x plus y, would give me u, and v would give me y. So it all works out. That is really the inverse. And so then at this point, basically, if I want to get my joint PMF of uv, f of uv, the kind of fancy notation would be a sum over all points x and y in a uv of f, now the joint of x and y. But this is really kind of way overboard notation, right? The only points in AUV is this one point. So this is just f, x, y, with, instead of x and y plugged in, we plug in u minus v and v. And we could have more complicated sums, but in this kind of simple case, that's all you get. And so we plug that in. Above, we had written our joint PMF. What's this thing? So let's plug in place of x, u minus v, and in place of y, v. What do we get? We get theta to the u minus v, e to the negative theta, over u minus v factorial, lambda to the v, e to the negative lambda, over v factorial. So you could leave it there generally. If all I asked was the joint PMF, that would be the answer. But we can do some simplifications because we actually get a nice result out of this. So let's just do a little bit of simplification here. So my little bit of simplification is that I'm going to combine these, and note that I can write this as 1 over u factorial times u choose v. So you probably believe that that's true. 1 over u factorial u choose v is the same as 1 over u minus v factorial times 1 over v factorial. That's pretty simple to verify. And we pull anything else out. We can combine. We can say this e to the negative theta plus lambda. Okay. And then we got a theta to the u minus v, a lambda to the v, and that's everything. Okay. So why am I bother simplifying? In this case, I could go one step further, and I could say, so this is the joint of u and v that we've derived. What's the marginal of u? Well, how do we get the marginal of u? Fu of u is, we sum the joint of uv, maybe a little lazy here, of uv over all possible values of v. What are the possible values of v? Now, certainly v can be 0, but it can never be bigger than u. So it goes from 0 to u. Why can't v be bigger than u? V is y, and u is y plus x. So u is v plus something positive. So u is always bigger. X is positive, x plus y, x plus v. So u is always bigger than v. So the possible values of v are from 0 to u. Right. V can be 0, it's kind of a Poisson, right? So the marginal of, if I ask you what the marginal of v is, that's really easy because we know that v is just y. But the harder one is, what if I want to get the marginal of u? And why would I want the marginal of u? The marginal of u is the distribution of x plus y. And that's interesting. Or at least I think it's interesting. I'll make a claim in a little bit. It's interesting. In any case, I want to get the marginal of u. So what I do is I take the joint, which we just painstakingly derived, and I sum across v. And so let's do this. Anything that depends on u and not v can be factored out. So I factor out the 1 over u factorial, factor out e to the negative theta plus lambda. The sum, v goes 0 to u, and what's left? U choose v, theta to the u minus v, lambda to the v. My claim is that by the binomial theorem, which we talked about, maybe way back when talking about the binomial distribution, the binomial theorem tells me that this is u plus v. No, it doesn't. It tells me it's theta plus lambda to the u. So go back and look at the binomial theorem, look it up, Google it. Binomial theorem. It's a little beyond the scope of this course, but it turns out it's useful. That we can write sum like this. This is just theta plus lambda to the u. And so what we're left over with here is 1 over u factorial, e to the negative theta plus lambda to the u. And the claim here, which isn't too hard, is you've got to recognize that that is a Poisson distribution where it has a rate parameter of theta plus lambda. Or u is distributed Poisson theta plus lambda. 1 over u factorial, e to the negative theta plus lambda to the u. It's exactly a Poisson distribution. Instead of x, I'm using u. Instead of lambda, it's theta plus lambda. So u it has a Poisson, marginally, it's a Poisson distribution of theta plus lambda. And u, of course, is x plus y, as a Poisson distribution. That's not how you spell Poisson. Poisson, theta plus lambda. So the theorem we basically just proved is that we started off where we had x and y are independent. X has a Poisson theta distribution, y has a Poisson lambda distribution. We went through a bunch of stuff, and we showed that x plus y also has a Poisson distribution. And to get the parameter for that Poisson distribution, I just sum together the parameters for the two marginals. So the sum of independent Poissons is Poisson. The parameter of the sum is the sum of the parameters. That's super nice. No reason that summing random variables has to stay in the same family or that the parameter has to be nearly as nice as just summing the parameter. But it is true for Poisson. So that's a kind of useful theorem that all statisticians and probabilists memorize. You sum independent Poisson, you get Poisson. Like you sum normal, you get normal. In this case, they need to be independent to be Poisson, which is not true in the normal case. But if you take a general distribution, I sum two betas, that's not going to be beta. Sum two gammas, not going to be gamma. But if I sum two Poisson, they're independent, it's Poisson. Okay, so that's an example of how to do this in a discrete case. And it's just basically the general principle from the continuous case, but now extended to two random variables. From the univariate case, extended to two random variables. In the last minutes here, let's look at the continuous case. And let's look at how we do this, the kind of transformation stuff in the continuous case. So again, our setup is we're going to have two random variables, u and v. There's some function, g of x, y, which you could write as component functions, g1 of x, y, comma, g2 of x, y. And assume a couple things. G is invertible. G is continuously differentiable in both coordinate functions. So it's continuous, and its first derivative is continuous. Continuously differentiable in both the coordinate functions. I'm going to write down the theorem, and it's going to be very analogous to the theorem we had in the univariate case. But bear with me again, I'm going to write the theorem in kind of its full glory, and then we're going to step back and discuss the components. So, we have the setup. I guess I should add to the setup is that x and y are continuous random variables. uv is some function g of xy. So here g is from the real plane to the real plane. G is invertible and continuously differentiable in both coordinates. Then, if all that's true, the joint PDF of u and v at some values little u and little v is, let's get this right, come on, the joint PDF of x and y evaluated at g1 inverse xy, comma, g2 inverse xy times the determinant, the absolute value of the determinant of the derivative of g, I'm going to write this, derivative of g inverse with respect to uv. Okay, let's put a box around that and talk about what that actually means. So the first part I think is pretty straightforward, right? So we want the joint PDF of uv. What we're going to do is take the joint PDF of xy, which we know. We're going to find the inverse coordinate functions, g1 inverse and g2 inverse, and plug those in. This is analogous to the univariate case, where if we had y was, say, g of x, so this is the univariate, then f of y we said was f, fy of y was fx of g inverse of y. And then we multiplied by the absolute value of the derivative of g inverse with respect to y. So the first part looks really similar, but now we have to have a more complicated notion of what a derivative is. And so replacing this derivative term here is this determinant of this, whatever the partial derivative of g inverse with respect to u and v is, and then an absolute value sign. So this thing here is what we call the Jacobian, this derivative. So generally, if we have a function h that takes in pairs of real numbers and spits out pairs of real numbers, so h of xy is some h1 of xy comma h2 of xy, right? Then the Jacobian is basically the matrix of mixed partials. Maybe I should say that better. The Jacobian is the matrix of partial derivatives of the coordinate functions. That's the technically correct way to say it. So you could say dh, d, and I'm going to, there are different notations for the Jacobian. Sometimes people just call it j. I'm going to say dh, d, xy. But it looks scary, but all it is dh1 dx, and the first row, dh1 dy. And then the second row is the partial derivative of the second function, dh2 dx dh2 dy. And so in our case, this Jacobian matrix, dg inverse, I'm writing like this, duv, is I find the inverse coordinate function, g1 inverse, and I take its derivative with respect to u. And then I take the derivative of that g1 inverse coordinate function with respect to v, and to do the same thing, we're going to take g2 derivative of the inverse of the second coordinate function with respect to u, and the derivative of the second coordinate function with respect to v. That's j. And it's a 2 by 2 matrix. It's a matrix of these partial derivatives. And the only last thing you have to remember is our friend's determinants. So we take this Jacobian, we take the determinant of it, and then we take an absolute value. So the determinant of a 2 by 2 matrix, the real quick review, is if I have a 2 by 2 matrix A, B, C, D, so let's call this matrix capital A. Determinant of capital A is AD minus CB. So I always think of it as this X, this minus that swoop. AD minus CB. So the steps for finding this, let's just write out the steps. So here we have UV is G of XY. Steps is 1, get the inverse functions, G1 inverse, G2 inverse. 2, find the Jacobian matrix, call it J, and get determinant. Supposed to read get. And step 3 is plug in formula. Man, I can't spell formula. Call it star. Our theorem, way back up here. Plug in this thing. Got the Jacobian, get its determinant, take the absolute value, plug in the coordinate functions, inverse the coordinate functions inside my known joint PDF. So it looks really scary, and it can be a little labor intensive, but it's not so bad actually. So in the last couple of minutes here, let's just start an example of how this might work. And next time we'll do a bunch of practice examples. So here's my example. I'm not even going to tell you what the joint distribution is. Let's just practice the steps. So I'm going to say UV is X plus Y, X minus Y. So that is U is G1 of XY, which is X minus Y, and V is G2 XY. Oh, I'm sorry, the first one is X plus Y, and the second one is X minus Y. So what are our steps? 1, get G1 inverse and G2 inverse. So how do you get the inverses? You solve back for X and Y. Notice that U plus V over 2 gives me X, and U minus V over 2 gives me Y. So what does it tell me? It tells me that G1 inverse of XY is U plus V over 2, and G2 inverse of XY is U minus V over 2. Step 1, get the inverse functions. Step 2, Jacobian determinant. That reads determinant. J, which is dg inverse DUV. Don't really care what notation you use, but you need to form this matrix, right? So let's just kind of write out what the matrix is theoretically and then kind of what it breaks down to be. So dg1 inverse du, dg1 inverse du should give me 1/2. dg1 inverse dv gives me 1/2. dg2 inverse du also gives me 1/2. dg2 inverse dv is negative half. Determinant of Jacobian is 1/2. 1/2 is negative a fourth plus, minus a fourth, which is negative 1/2. So the absolute value of the determinant of Jacobian is 1/2. And step 3, plug in to formula. So f, the joint PDF of u and v at little u, little v, is joint PDF of x and y at g1 inverse uv, g2 inverse of uv times absolute value of the determinant of Jacobian. In that case, I haven't actually told you what the joint is. Something, fxy, whatever it is, inverse, g1 inverse is u plus v over 2, g2 inverse is u minus v over 2, and that absolute value determinant is 1/2. So that would be your answer. In reality, you would be at half and you would know some fxy, but in our case, we don't quite know it yet. But that's the deal. So let's stop there for this lecture. And next time we'll pick back up and do a bunch of examples of bivariate transformations.